Modern electronic packaging is defined by a physical conflict. Engineers are steadily increasing processing power and high-frequency communication within devices, while simultaneously shrinking the physical chassis that houses them. This creates conflicting mandates. The individual components require strict electromagnetic isolation to prevent crosstalk and signal degradation, yet they must also be tightly coupled to the metal chassis to dissipate intense heat. The physical problem lies in the empty space itself. Ambient air is an excellent electrical insulator, but it is a terrible thermal conductor. Relying strictly on mechanical contact between a rigid chip and a heatsink leaves microscopic air gaps caused by the natural roughness of both surfaces. Those trapped pockets of air ruin the thermal performance of the connection. At the same time, microscopic gaps around chassis seams and protective shields act as apertures, allowing high-frequency RF leakage to escape and interfere with adjacent circuits. System stability no longer relies solely on how a printed circuit board is laid out. It requires highly engineered interface materials to actively manage energy flow at the microscale. The empty space between components is the critical architectural layer in modern device design. It dictates whether a high-density system survives or throttles itself to prevent physical failure. The first major threat in these environments is electromagnetic interference, or EMI, radiating from high-speed DDR memory and camera processors. EMI refers to electromagnetic disturbances that can disrupt the operation of nearby electronic circuits. In ultra-dense spaces, traditional metal shielding fails to solve the problem. Reflecting RF noise back into a tightly packed cavity forces the waves to bounce, causing internal resonance and severe signal degradation. The Monero noise suppression sheet, specifically the ACP and AH series, provides an active absorption alternative to passive reflection. These sheets are constructed using physically refined, magnetically oriented alloys. These alloy particles are suspended evenly within a flexible polymer matrix. This diagram shows the mechanism of action. When an incoming electromagnetic wave strikes the sheet, the magnetic domains absorb the wave and convert it directly into a negligible amount of thermal energy. The ACP series is engineered to effectively handle broad-spectrum noise, suppressing frequencies from 50 Hz all the way up to 24 GHz. Managing high-frequency EMI in confined spaces requires materials engineered to destroy energy through physical conversion, rather than allowing it to continuously reflect inside the housing. Transitioning from internal component noise, engineers still face the challenge of grounding components and sealing the outer metal chassis against the remaining RF leakage. The specific engineering requirement here is continuous XYZ axis electrical conductivity that holds its integrity under highly variable physical compression. This technical diagram shows the Minoru CG200F foam-on-foam conductive gasket. An inner, highly compressible polyurethane foam core bridges uneven gaps. A gold-plated woven fabric wrap ensures continuous surface conductivity, while the base conductive pressure-sensitive adhesive securely bonds the gasket, maintaining the grounding path. This structure achieves greater than 85 decibels of shielding effectiveness. Shielding effectiveness, measured in decibels, indicates how much the material reduces the power of an electromagnetic field. This is paired with a Z-axis electrical resistance of 0.01 ohms or less. Extreme mechanical flexibility is a mandatory requirement for maintaining an unbroken electrical shield across the unpredictable physical tolerances found in mass manufacturing. Moving from electrical shielding to thermal management, the next critical bottleneck exists directly at the surface of the integrated circuit. Extracting heat vertically along the Z-axis into a heatsink requires zeroing out the interfacial thermal resistance caused by the microscopic surface roughness of the components. Minoru's JTGF series, a line of one-part silicone and ceramic gap fillers, is formulated to bridge these irregular microgaps. Specific formulations in this series achieve thermal conductivities up to 13 watts per meter Kelvin. This unit, watts per meter Kelvin, quantifies a material's ability to conduct heat, where a higher value indicates more efficient energy transfer. A liquid dispensed filler offers a distinct mechanical advantage over a rigid thermal pad. The low modulus paste-like consistency minimizes the mechanical stress placed on delicate integrated circuit packages during initial assembly. This low-stress property remains critical over the entire lifespan of the device. The filler material passively absorbs the microscopic expansion and contraction caused by continuous thermal cycling without fracturing. Optimal Z-axis cooling requires an interface material that behaves mechanically like a compliant liquid to fill the voids, but thermally like a solid to move the heat. The primary packaging constraint occurs in devices like mobile OLED displays, or COF packages. COF stands for chip on film, where the integrated circuit is mounted directly on a flexible polymer circuit. In these designs, there is simply no vertical room for a traditional Z-axis heatsink. When the Z-axis is physically blocked, heat must be forced horizontally along the XY axis to prevent local failure and physical warping. The Minoru 51XXX graphene soaking material is a highly anisotropic solution designed specifically for this horizontal heat transfer. Anisotropic materials exhibit physical properties that change depending on the direction of measurement. The base structural layer of the material is highly ductile rolled copper, which provides the necessary physical flexibility to fit into tight footprints. The copper surface is treated with a specialized graphene coating. This enhancement layer defines the thermal profile of the copper, creating a specialized path for directional heat transfer. This vector chart represents the material's anisotropic thermal data. Vertically, along the Z-axis, the thermal conductivity sits between a standard 4 and 20 watts per meter Kelvin, revealing the critical metric. The horizontal XY axis thermal conductivity reaches 1,910 watts per meter Kelvin. The functional result of this disparity is aggressive thermal routing. A pinpoint localized heat source is instantly stripped of thermal energy, spreading it rapidly across the entire wide surface area of the sheet for passive convective cooling. Artificially manipulating the directional flow of heat allows engineers to bypass physical Z-axis space limitations entirely. Looking back at the fully assembled, high-density device model, the function of these individual layers becomes clear. The hardware packaging bottleneck is solved by combining these disparate anisotropic materials into a unified system. Low modulus gap fillers actively pull heat vertically off the core processors. Simultaneously, FOF gaskets seal the physical chassis seams, maintaining an unbroken electrical ground. Graphene tapes aggressively spread heat horizontally under components where vertical heat sinks physically cannot fit. And noise suppression sheets cap the high-speed memory, actively absorbing internal RF resonance before it degrades the signal. Because of these dense, microscale interactions, thermal management and electromagnetic compatibility can no longer be treated as separate engineering disciplines handled by distinct components. In modern electronics, these microscopic interface layers function as the architectural foundation that dictates the device's operational limits.